And here's the second video for integration by substitution, and we're doing some more challenging tasks. Make sure you've caught video 1. Okay, so we've got the integral of 2x plus 1 over 1 minus 2x all squared dx, and we're going to use substitution. But what do we let u equal? We're going to let u equal the function within a function, because that's the method we've been using, and we're going to continue to use that on this one here. So let u equal 1 minus 2x du dx would be negative 2 so a half du is the same as dx. Now also on this one, if we go back to this initial statement here, this is where questions like this vary slightly. Sometimes these are called linear substitutions. Okay, that's often the tag that goes along with these. So sometimes they're referred to as linear substitution style questions. Now what we do there, where the asterisk is, we're going to write things in terms of something that's evident here in the integrand. Okay, now we don't want a combination of x and u in the same question. What we want is it to all be in terms of u so we can integrate it more easily. We want to be able to write this. So using that u equals 1 minus 2x, we could also write that 2x equals u minus 1, and what we have on the numerator is 2x plus 1, so 2x plus 1, oops, sorry, hold there, made a mistake. What should that have been? 2x is 1 minus u, sorry about that, and 2x plus 1, which we have evident on the numerator of the integrand, adds another 1 onto that, so we could write that as 2 minus u. Okay, so keep that, save that for later, that's going to be handy in just a second. So let's go back to the expression and do some substitution now. So we indeed have 2 minus u on the numerator, and what do we have here? We've got a substitution, we've got u instead of 1 minus 2x, so we have u squared on the denominator. Now this du here, this du can only be written, oh, I've spotted another error. Have you seen it? Maybe you saw it before. Okay, it's on this line here, so that dx, that should have been a u, dear oh dear. Wow, it happens. So to replace dx, we must in fact not replace it directly with du, we have to replace it with negative a half of du. So we could put that negative a half out here if we like, and that's what we're going to do. Okay, moving down a bit. Now, like you might have seen previously in some of my videos, we can split that numerator up into 2 over u squared. We can take the integral of that, and the u subtracted off, the integral of u over u squared. Okay, so analytical time now. Alright, we got two, bit like previous video, we've got 2 different integrals and 2 different methods we could use for each of them. That's why we split them up, you see. And first one really is better if we just write it as something in index form. That's going to be pretty easy to integrate. Next one there, if we think about our old friend and ally f dash of x over f of x, when we integrate that, we get log of f of x plus c. Alright, so that looks like it, doesn't it? Because if we have the f of x equals u squared, f dash of x would be 2u. Now we could put a 2u up there. We have changed it, of course, haven't we? So we have to compensate for that. We've doubled it, so we have to halve it out there. Okay, but that's not going to be tricky to integrate now. So we've done a lot of the heavy lifting. Close the square brackets there, because it's all multiplied by -1/2. Okay, so we have, with this first integral, we add 1 to the power and divide it by its new power, which would be -1. Okay, so we have -2 there. Now I'm going to distribute the -1/2 through at this point as well. And we've got minus negative, so we've got a plus, a quarter, and we've got log u squared. So we've got a quarter natural log of u squared. Let's tidy that up a bit. Alright, and plus c. So negative times negative makes positive, so we've just got u to the -1 and plus a quarter natural log u squared plus c, and we've got to substitute back in terms of x again. We've got 1 minus 2x to the -1 plus a quarter natural log, sub that back in terms of x. Okay, on the homeward stretch for this question now. Okay, so we've got 1 over 2x here, and using log law 3, we could say it's that 2 could multiply on the front 2/4 is 1/2 natural log 1 minus 2x. I guess you should probably write the absolute value around that one there because it's linear, and it's plus c. Okay, 1 to go. Okay, the fourth and final example in this pair of videos, we've got an interesting activity here, and look, this is not strictly content you must know, because this video is being made for Queensland U12 Specialist Maths Unit 4, and this is something you might see at a university degree or some rigorous course anyway. It might be early, maybe first or second year stuff if you do a calculus-based study. But we're looking at an alternative way of showing this result here. We used different methods early on with finding the derivative and the nature of inverse trig functions to find that result. We're going to do what's called a trig substitution to also get the result, and trig substitutions further down the track will be important because you'll be able to integrate things that we currently can't do that are beyond the scope of our course. So it's not essential, but it might be handy. It's worth looking at anyway, because you can always learn something useful. Okay, it might be useful in an unexpected way. So this is optional. What we're going to do is show the first one. When you have square root of a squared minus x squared somewhere in the integrand, a trig substitution of x equals a sine theta will help you move forward. Okay, that's the one this video is going to focus on. There are others that do exist, namely these ones, and you make those substitutions there. Okay, we won't be covering those bottom two. And it just allows you to do things that are currently beyond the scope of the course that this particular video is aimed at. Okay, so if we've got, let's say this one here, we've got 1 over the square root of 9 minus x squared. If we have to integrate that with regards to x, we know from all the work we've done in the past that the answer is just going to be x over 3 because a equals 3. So need inverse sine or arc sine x over 3 plus c. And so let's start this little investigation here. So we could have use this to arrive at that same result, and it actually helps showcase some good maths in here. So if a equals 3, since a squared equals 9, we're going to let x equals a sine theta, and a is 3, so x equals 3 sine theta. Now, a couple of things at this stage. If we have x equals 3 sine theta, we can say that sine theta equals x over 3. And theta equals inverse sine or arc sine x on 3. That kind of looks familiar, doesn't it? Theta equals inverse sine x over 3. If we go back up here, alright, okay. Anyway, we can also say that x squared equals 3 squared 9 sine squared theta. And dx d theta equals 3 cos theta, or dx equals 3 cos theta d theta. Alright, where am I going with all this? Oh heck, I don't know. In fact, yes I do. We can use all of that stuff we've just developed and we can make a substitution into the question we're doing. So we've got, instead of x, we've got 3 sine theta. So we've got under here 9 minus 9 sine squared theta. Okay, and that's got the square root taken, and we've got a substitution here. For dx we need to write in 3 cos theta d theta. So we have to bump that 1 that's there, and we have 3 cos theta d theta there, and put our summation symbol in. Okay, we're going to manipulate the denominator now. So what I mean by that is we've got a factor of 9 there, factorise that denominator. We've got 1 minus sine squared theta. That should sort of ring a bell. Okay, and that means we've got We've got 3 cos theta on the front. We can separate the two parts of the product under the radical sign. So we've actually, part of it is the square root of 9, which we can write as 3. And we can write 1 minus sine squared theta using the Pythagorean trigonometric identity. We can write that as cos squared theta. So it's still got the square root on it. I've already taken the square root of the 9 to get that 3 there. Okay, and we can divide through top and bottom by 3. It's always satisfying, and we've got cos theta. Now, well, if we've got cos squared theta, then you take square root. That's cos theta all squared square root. So you just got basically cos theta over cos squared theta, or cos theta, square root of cos squared theta. So really it's just the integral of that, which is the integral of 1 d theta, which is theta plus c. And you're thinking that's not the result we had before. We had some inverse sine thing in it. But remember, what did theta equal? Theta equaled, can you see it there? Inverse or arc sine x over 3. Okay, which is, from that direct result, arc sine x over 3. So, arc sine x over 3. Okay, so perhaps at the level that you're studying at right now, you might not be able to see a purpose, but there are questions that don't match anything we've covered, and you can use those three trig identities in the future to give you another set of tools.